So just to summarize the testing procedure, in hypothesis testing, the first thing you do is to set up the null hypothesis, or H0. This is the status quo. This is how things are running. We then select an appropriate alternative hypothesis, or H1. This is the new claim. We choose a level of significance, and generally this is going to be a small value, alpha. And we choose an appropriate test statistic. So the one we're looking at in this case, we're looking at mean values, and we look then at our X bar as our test statistic. We design the test by specifying the critical region, and we select a sample from the population and compute the value of our test statistic. If the observed value of the test statistic is in the critical region, then we reject the null hypothesis. Otherwise, we do not reject. And there is a final step, of course. You should interpret your results. Do you need to do additional tests? Does the example make sense? And what would be your next steps? So I would like to do, though, I take one more look at the designing of the test now that we've reviewed again the concept of the test statistics. So once more, we have a distribution H0 around a mean, mu0. Now we have a claim for our rope example that our product has a higher mean. And we have decided to choose, you remember, an alpha level, a Z alpha level, such that this value here is very small. This is that we have a low probability of accepting the claim when it is not valid. So this is going to be the probability of a type 1 or 2? Type 1 error. The probability of accepting the claim H1 when it is not valid can also say the probability of rejecting the null hypothesis when it is valid. We want to keep this small. Now, if you look, the probability of a type 2 error, my picture here is going to be here. This is beta, the probability and here the probability of the type 2 error. It depends on where the new distribution is located with respect to H0. We fix alpha. And beta, of course, then is the probability of rejecting the alternative hypothesis, the H1, even though it's valid. So if we look at this again in terms of the test statistics, if we calculate a test statistic that is here, we will look at that with respect to our z-value, and we will say we will not reject H0. But it could be that we have stronger rope. Could be that the supplier is right. And it's just as unfortunate for the supplier that his sample that was taken was not strong enough to convince us. His sample did not lie in our critical region. So the supplier maybe should do another test. But depending on how far away our distributions are, that depends then how big our beta value is. And to protect the consumer, we're more interested then in specifying our alpha value. So we specify alpha, and then depending on how the distribution is for the claim, that will determine how large beta is. So I hope that shows a little more clearer these ideas of producer's risk and consumer's risk. Now, one last small point. For our examples, we chose an alpha level, which allows us to say that a hypothesis is accepted or rejected with an alpha level of significance. So again, alpha here. For example, we say the null hypothesis that mu is equal to mu0 was rejected at a 0.05 level of significance. But this actually does not tell us if the measured statistic is just barely passing the test or not. It doesn't tell us if we are here or if we are here. It doesn't tell us if we have just passed the criteria given by alpha or if we have our sample gave us a z-value that was so much bigger than our mu0 that we could easily accept the new claim. So if a computer program, though, is used for hypothesis testing, in addition to calculating the test statistic, the computer program will also give a p-value, the so-called p-value. So what is this p-value and how can we interpret it? The definition of the p-value is the probability in the distribution of the test statistic that lies beyond the observed value, away from values favoring the null hypothesis. If the p-value is smaller than the chosen alpha, it means that the observed value of the test statistic lies in the critical region, and this means the null hypothesis should be rejected. If the p-value is larger than alpha, then the observed value is not in the critical region, and the null hypothesis should not be rejected. And this is maybe easier to see if we look at this one-tailed test, as we've shown here. So here we have the observed value of the test statistic. And the p-value is this entire area lying away from the values which would favor the null hypothesis. And that area, as we can see in this example, is greater than the area that corresponds to our alpha value. So we find the p-value by calculating the probability in the test distribution that lies away from the null hypothesis. And here we see that this area, this probability, is greater than the probability that we've chosen for alpha. And we cannot then reject the null hypothesis. Our observed value does not lie in the critical region because we see that the p-value is greater than alpha. If the p-value were smaller than alpha, then it would lie, the observed value of the test statistic would lie inside the critical region. And then we would be able to reject the null hypothesis. And why is that useful? Because the p-value provides more information about the test result. It can tell us if we have passed the test definitively, if we have a value that lies well within the critical region, or it can tell us if we have, say, passed the test, if we can reject the null hypothesis with beyond the 95% level that we've defined by alpha. It can tell us much more than just looking at the comparison of the test statistic compared to the critical value for Z.